Hi everyone. In this activity, we're going to continue learning about data visualization with the ggplot2 package. So specifically, we're going to look at how we can conduct exploratory data analysis to familiarize ourselves with the new data set, how we can use the geom point and geom smooth functions to create a scatter plot with a line of best fit, how we can apply what are called complete themes, essentially pre-bundled sets of customizations to customize the appearance and overall look of our ggplot2 visualizations, how we can modify what are called theme elements of ggplot2 objects to further customize those to our desires, how we can create bar charts using different geoms in ggplot2, and how we can incorporate additional variables into our visualizations using what's called faceting, and how we can combine multiple plots created with ggplot into a single image using what's called the patchwork package. So the first step, as usual for this activity, we're going to load some packages that we need. And purposely, I have the patchwork package unavailable on my machine here to show how we need to install that as a quick reminder. So you may need to install some of these packages if they're not currently installed on your laptop already. So let's get a new R Markdown file opened up if you haven't already, and saved where you want. And then let's start the activity by loading some R packages. So insert a new code chunk, paste this code in with all these library commands, which load these R packages. Okay. If one of these R packages is not installed, you may see a pop-up like this show up that says, would you like to install it? You can click install and do it that way. The pop-up doesn't always show up, in which case you may need to run install dot packages, plural, in the console and put the name of the package in quotes as a reminder. So here I'm going to install the patchwork package by submitting this to the console, install.packages patchwork, hit enter. And now R is installing that package to make it available. So you may need to do this for several packages, likely the risk communicator package, ggpub_r. Okay, so you'll have to go through this process for each of these. Once you've installed all the packages and they're available, you should be able to load all these packages, and you can check that by running this code chunk here by clicking this green triangle. And then we see these warning messages. That's okay, as long as we don't see the word error. Okay, these are just messages letting us know that some packages have functions that are called the same thing. The dplyr package has a function called filter, but the stats package also has a package called filter, so it's letting us know that it's defaulting to the dplyr version of the filter function if we call it. Okay, that's what all these messages are for, but nothing to worry about. Okay, so once we have these packages loaded, next we'll take a look at the data set we'll be learning about in this activity. So this is a data set from a real-life public health study called the Framingham Heart Study, which first began in 1948. I studied biostatistics in grad school myself, so this was a data set we visited a few times in classes, and I thought it was really interesting, which is why I chose to incorporate it in this activity. So this heart study is what we call a longitudinal study, since participants were enrolled in the study first in 1948 and then followed for an extremely long duration of time to see long-term trajectories and outcomes and characteristics about these people. This study has continued so long that is turned into a multi-generational study, and that the children and grandchildren of these people have some continued to be measured and assessed to collect data for this study as well. So the initial goal of this was to explore different characteristics and factors associated with the risk of cardiovascular disease in general. But over time, this data has become so useful from the Framingham Heart Study that researchers and public health experts have used it to analyze things like familial trends in cardiovascular disease, but also looking at genetic factors now that we have the advent of genetics data being more readily available. So exploring associations with different genetic traits and different health outcomes. Like many studies that were conducted earlier in the 1900s like this sample wasn't the most representative of the general population in the US. It was very much white, mostly male, and as the name suggests, just included people from this one city, Framingham, Massachusetts. But when doing a study like this, it's important to keep in mind that one city's results might not generalize to the greater population of the US, right? Grand Rapids, Michigan is likely very different than Sacramento, California, for example. So it's important to have some more diversity and representativeness in your samples if you want to generalize that, which often we do, to a larger population. Okay? This helps us not only use our results for a broader set of people, it also just generally improves our understanding of some of the mechanisms underlying these diseases, because we have to account for many factors when exploring these things. So important for many reasons. So they've included more diverse participants, a broader set of people moving forward. So an earlier version of this data set is available in R via the risk communicator package. Okay, so let's first load this data by using this code here. And if we run this code, after we run it, we can see this object called Framingham in our environment pane in the top right here. We can learn more about this data set. Since it's a data set made available via an R package, those often come included with documentation files or help files. So if you submit $Framingham, and the capitalization is important here, to the console, we can see the corresponding help file that the creators of this R package made. So this will be helpful for learning even more about the study and more about the different variables in this data set. So for example, we can see here that it has roughly 11 or 12,000 rows in this data set and 39 columns or variables. Here's the different variables: RAND ID, a unique subject ID, the sex of the participant, the total serum cholesterol measured in milligrams per deciliter of each participant, okay, the age in years, and so on. So all the variables have descriptions here, and we can learn more about that data set by consulting this help file. So one thing that will be helpful in particular is recoding some of these variables to be a bit more descriptive, and also to subset the data to a smaller table of data to start to make it a little more manageable to work with. So let's create a new object called Framingham sub that contains just the first 10 variables from the Framingham dataset. And we can do so using the select function from the dplyr package. So we'll say Framingham type dplyr : select, all lowercase. And to get the first 10 variables from the Framingham dataset, we can use this syntax 1:10. The select function allows us to subset the columns of a table of data. We run that code, and you can see the Framingham sub object now in our environment pane. And if we click on that, we can take a look at this. So here we can see all these variables. We have the random ID. If we look at the help file, okay, we can see that for this data set, the sex variable is coded as 1 representing males and 2 representing females. So they didn't explicitly write out the strings. They used numeric encodings of these values, okay? So this is a categorical variable, but it's numerically encoded. And often that can be to take up less space with storing the data set, or it makes it easier for entry for the researchers when entering that data manually. Right. But for our purposes, for data visualization and getting summary statistics, we want this to be more descriptive than the numbers 1 and 2. That can be a little bit confusing for people looking at our plots, right? So we're going to update this variable to reflect that more descriptive values. And so we'll do that using the mutate function. So first, we're going to update the sex variable to re-encode it instead of 1s and 2s. Okay. I'm going to copy this code from before. We're going to add a call to the mutate function. And so what we're going to do is we're going to say sex equals case when. So we have multiple cases we want to consider here. When the sex variable is equal to 1, we want to relabel it as the string male. So we say sex equals 1 tilde the string male, comma. Sex equals 2 string female. Okay, so how case when works generally is within the mutate function, most commonly is where we use it. I'll write like a more general piece of code that won't be functional here, but just to demonstrate it. We have a new variable we're creating. It can be a function of an old variable, which these can be the same ones themselves. And we have some condition, essentially. We're checking if it's true or not. And if this condition is true, we assign this value to the new variable. If that condition 1 is false, we check a second condition typically. And then we'll assign a different value. And this will go on until you have many conditions, however many you need. And then typically you have a closing condition, we call it a catch-all, that is always true, which we do by just having all caps true. And then we'll say like it's the final value we would assign to the new variable. So that's the general structure of how case when works, which can conditionally assign a value depending on different conditions being true or false. So here our condition is whether or not sex is equal to 1, and we check equality in R with 2 equal signs. And the second condition is if sex is equal to 2. So this code right here I have highlighted isn't functional, it won't work, so I'll get rid of it now. But that's the general idea of how the case when function works. So you can check this out here. Let's add that final catch-all condition. So for every other case, we will just say NA. And if we run this, you can take a look at Framingham sub. Okay, and let's see how that looks. Now we see instead of 1s and 2s in the data, it says male and female. Okay. And if we opened up the original Framingham data set, we can see, okay, the first two cases were males, and then it was a female. Let's make sure that that lines up, that that was reassigned properly. So if we open up Framingham, we can see 1 and 1, and then a 2. Male and male, and then a female. So that seems like it worked properly, right? Doesn't prove that it worked for all 11 or 12,000 rows, but checking the first several is a good a good starting point. Right? So we successfully relabeled this variable to be a bit more descriptive. Now let's also do this for the current smoking status variable. Okay. So currently the smoking status variable is coded as 0 for a not current smoker and 1 for a current smoker. Okay. So let's recode it as 1 for yes and 0 for no. So we can do this by copying this code that we previously wrote, adding a comma inside this last parenthesis, return. You can make multiple variables at once or modify multiple variables at once inside one call to the mutate function. So in this case, we're going to be updating the cur smoke variable this time. And be careful with your capitalization. Capitalization of variable names is important in R. It's case sensitive. The spacing is actually not too important, but I'm fixing it here for readability. So we want to update this cur smoke variable now. And we say if it's 1, we want it to say current smoker. So, and we were saying we're calling that yes. And then if it's 0, okay, so make sure you update this 2 to be a 0. We want it to say no. Otherwise, NA, which is a missing value. Make sure you update this 2 to be a 0. That's an easy thing to forget here. If we run this, we can see now that in the Framingham sub data set, okay, current smoke, no, 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 no. First 4 are no. If we look at the original data set, 0, 0, 0, 0. Okay, it doesn't have a smoker until the 6th row. And that matches how we coded it here. So it looks like we successfully recoded this variable as well. Okay. So now that we've recoded those variables, we're going to continue with using this Framingham sub data set for the rest of the activity. So next, we're going to use a function called skim that's very useful for getting acquainted with a data set when you first are opening it up. I highly recommend this function if you have like a timed data science interview or just anytime you're acquainting yourself with a new data set. It's very efficient. So if we use skim, and then we're going to do this on Framingham sub, okay. Skim is meant to be used when knitting to HTML primarily. It does work when you're knitting to PDF or Word, but the output can look a little bit scrunched or crowded. So I would recommend knitting to HTML. It's also not code that looks great when you run it interactively. It's meant to be used when you knit or compile the whole document and look at the corresponding output. Okay, so let's knit this whole document and then take a look at what we get from the result of skim. So the result from skim me zoom in a little bit here. Gives us a few things. So here's the code. We can see it tells us how many rows or observations in our data set, how many variables or columns, the number of variables of each type. So here we can see we have 2 character string variables and 8 numeric type variables. The only character strings are the ones that we changed or updated to be strings, since everything was numerically encoded before. Okay. So it tells us there's 0 missing values for each of the sex and the current smoking status variables. There's 2 unique values for each of them. And the min and max are the min number of characters in the string for any value and the maximum number of characters. Okay. Looking at the numeric type variables, we can see lots of summary statistics about our data set here. So we have the variable name, rand ID through diabetes, and then we have the number of missing values. So for example, rand ID was entirely non-missing, but total cholesterol had 409 missing values. Okay. Always a good idea to be aware of missing values when looking at your data set. This is something, in my experience in particular, in data science interviews, for example, people like to try and trip you up on. There might be a bunch of missing values thrown in for a particular variable, and it's sort of like a trap. Like the data science interview person wants to see, are you actually going to analyze that variable and act like everything's okay, just proceeding along, not really mentioning that, hey, maybe there's 95% of the values missing, right? I had that happen in an interview once where one variable, they sort of were leading you to analyze it, but it had 99% of the values missing, right? So it was a trap. They wanted you to say, the variable is missing too much data. We need to look into this further and investigate what happened here, rather than making strong conclusions and statements about it as if it was reliable. Okay. So always something to look out for here. The raw number of missing values is good to look at, but what's arguably more important, in my opinion, is the proportion of missing values. In this case, 409 might sound like a lot of missing values, but because we have 11 or 12,000 observations, actually 96% of the values are still there. Okay, that's this completion rate. Or for example, for the cigarettes per day variable, sig p day, 79 might sound like a decent number of missing values, but actually 99% of the data is there. So for these variables, in my opinion, I might mention that there's some missing values in like a data science interview task, but I would still analyze them. In general, like my rule of thumb for like a cutoff point is maybe like 70 to 80%, I would still consider analyzing that variable, but I would always make note if there's missing values, and just acknowledge that there's caveats or limitations to any findings due to missing values being present. The data might not be representative of the population that you're interested in. Here, not too much of a problem though. In addition to metrics about missingness, Skim also tells us summary statistics for the variables. So we get the average or sample mean, the standard deviation, the percentiles, starting with the 0th percentile, more commonly known as the minimum value, and the maximum percentile, the 100th percentile, also known as the maximum value, 50th percentile, which is also known as the median. Okay. And then we have even a tiny little histogram in here, which I don't know how useful that is for the most part, but it's kind of fun to look at. And it's pretty neat that they were able to get a histogram in a table, I guess. Okay. So this skim function can be really efficient in terms of time of getting yourself acquainted with a data set very quickly and identifying possible issues, right? Another thing that I would look for that was thrown as like a curveball at me in data science interviews, for example, I was given a task analyzing a data. They threw in a bunch of missing values like that to see if I would catch it, right? Skim helps you catch that. They also threw in an extremely large value, right? So for example, I had a data science interview at Target, and the data was on sales, the amount of money that a customer spent in a trip to Target, right? And they threw in a value that was so extremely large. It was like over, $100,000 or something like that. And it was supposed to be just at a regular Target store. So they were wanting to see if I would just calculate averages, or use a linear regression model or other methods and ignore the fact that there was this extreme outlier in the data set that had to be a typo or is something wrong there with that value. There's no way somebody spent that at Target. Okay. They wanted to see if I would at least acknowledge it. Probably what's best when you know that a value seems not sensible is to exclude it from the data, run your analysis without it. And if you think there's some possibility it's a legitimate value, you could also run like a second analysis where you still include it and discuss how the results change, right? But like in that case, they were wanting to see that I recognized with some common sense that that value made no sense and that I would not use it, right? So that's another thing to look out for as well, is extreme outliers. And the best thing to look at for checking that out, the minimum value and the maximum value, okay? Those give you the boundaries on your data set, right? So Skim can help you very quickly identify possible issues with your data and better acquaint yourself with your data sets. So now that we've used Skim, I'll give you a moment here to try and set a complete theme, okay, using this code. Running this code in a code chunk. And then try and make a basic scatter plot using the variables for diastolic blood pressure and systolic blood pressure. Okay, so try this on your own for a moment. Pause the video, try this on your own, and then unpause the video and we'll look at it together. Okay, so hopefully you were able to try that. So let's set a common theme for our entire document using this code here. So this function allows you to set a constant theme for the rest of your activity. So at this point on down in your R Markdown file, this specified ggplot theme will be used for all ggplot2 visualizations that we create. Okay, so if we run that here, we don't see any noticeable changes, but we will notice it in the visualizations that we create. So next, let's make a scatter plot. Between diastolic and systolic blood pressure, faceting by the sex of the participant, setting the alpha aesthetic to be 0.2, which controls the transparency of the points. And then we're setting altering the legend of the document to exclude aspects about the color of the points. So we're going to use the ggplot2 function. We're going to pipe the Framingham sub data set into ggplot2. And specify our x and y variables. And so to match the activity, we're going to put diastolic as our y variable and systolic as our x variable. We're going to add a geom point layer to make a scatter plot. Okay, we can already take a look at that preview, see how that looks. Okay, we can see our theme has been applied, theme view. Now we also want to facet by the sex of the participant, so we can do that by using the facet grid function. So we're going to say facet grid tilde sex. We want to facet by the sex of the participant. Okay. The general structure of the facet argument is, I'll do this in the console. So this is not going to be code that actually works. We want a variable that will determine the rows of the faceting, the subplots that we make, and then a variable that determines the columns. And you can just have one variable if you just want, in this case, like we just wanted it for the columns, but we're not faceting by the rows at all. Okay, but for example, we could facet based on the smoking status for the rows as well, and we get this 2x2 grid. Okay, where we have smoking status no, smoking status yes, right? You can facet by up to 2 variables like that. Okay. Here we're just going to do it for the sex variable. And then since this data set has so many points that are very close together, what can happen with ggplot is you have this like black cloud of opaque color that you can't really see the finer details about what's going on with the distribution of these points. So we can alter the transparency of the points to better show finer details or aspects about the distribution of these points by using the alpha aesthetic. So typically, you'd have to play around with this value to try out what's a good value. I played around with this a lot before filming this video. We're going to set the alpha aesthetic because we're not mapping it to a variable. We want it to just be a constant value. We're setting alpha aesthetic, so we do it inside geom_point to be 0.2. You can see how the transparency of the points now is different. We can see a little bit more detail in the distribution of the points here. And then we are going to next, we are going to color the points also, okay, based on the sex of the participant here. And so we are mapping the sex variable to the color aesthetic. So we do that inside AES. So we'll say color equals sex of the participant. Okay, now if we run that, we can see Hadley's default colors that he uses, which as a reminder are not colorblind friendly. This is a good case of a redundant legend. The faceting already tells us that these points are for the participants who identified as female, and these points are for the participants who identified as male. So the legend doesn't give us any additional information, right? It's redundant. Whenever possible, we want to get rid of redundant legends because it's unnecessary information added onto our plot that can potentially leave your viewer wondering, oh, was I supposed to know something additional here? Was I missing something in reading this plot? It can just cause potential confusion. So it's best to suppress legends whenever redundant, to suppress redundant information. That can be done a few different ways with the code. One way is to add this guides color equals false layer. and that will suppress the legend. Next, we're also going to have the size of the points be a function of the number of cigarettes smoked per day, sig_p day. And we're going to use a colorblind friendly palette since the default colors for ggplot are not colorblind friendly. Always a good thing to do. So let's copy this code from the previous part. To map the number of cigarettes per day to the size aesthetic, we're going to do that inside AES since we're mapping an aesthetic or connecting an aesthetic to a variable in our data set. So we're going to say size equals sig_p day. Okay, now you can see that that will show up in the plot. Okay, larger points mean that participant smoked a larger number of cigarettes per day. Smaller points mean smaller number of cigarettes per day. Okay, ggplot gives you a message that, hey, 79 values were missing in at least one of the variables in this visualization. So each point has several variables associated with it here: diastolic blood pressure, systolic blood pressure, the sex of the participant, and then now the number of cigarettes per day, all measured about each one of these data points. If any of those are missing, ggplot's default behavior is to just exclude it from the plot. Okay, it's just not shown. So that's okay here, but it's just something to note and a potential limitation in terms of patterns that we're seeing in the data, right? So let's also add this colorblind friendly palette, which we can do here by using a scale color colorblind layer. And if we run it with that, okay, this is from the GG themes package. We had to have that loaded to have this function available. Now we can see this black and orange color scheme that we have going on. Okay. And let's also move the legend to the bottom of the plot. So we can do that by adding a theme layer and saying legend.position equals, and then in quotes, bottom. And again, the capitalization is important here. This is case sensitive. So it's all lowercase for that layer. Okay, that throws that legend at the bottom, a little more readable being horizontal like that. Okay. Now, the other thing we want to update here is all these plot labels, right? We don't want to just have it say dia-BP. We want it to say diastolic blood pressure and to include the units of measurement when possible. So we can see from the help file, diastolic blood pressure is measured in millimeters of mercury. So let's have that be shown and let's match the activity, essentially, how it's labeled. So we're going to do that by adding a labs layer. Let's do it before the theme. Typically, when you add a theme layer that customizes fine aspects about the plot, you want to have that be the very last thing that you add onto the ggplot as a layer. Everything else goes before the regular theme. Let's add this labs layer. We're going to customize the title of the plot. So we're going to have that say diastolic, systolic blood pressure. Okay, I'm using a passive title here by just sort of describing the variables that are in the plot. Okay, I've gone to a lot of different R workshops and data visualization workshops over the years, and I also like to follow data scientists and statisticians, biostatisticians on social media. I know some people have strong opinions about titles, right? So, for example, some people are okay with these more passive titles because it makes takes a more objective approach. We're not trying to bias the viewer into some result that we found or some viewpoint on the problem. But I've also heard strong opinions from others that they say you should be very particular about what the main takeaway from the plot is and what the viewer should be looking at. Like what type of trend or pattern should the viewer be observing in the plot? So saying something like a positive linear trend between systolic and diastolic blood pressure for all participant sexes with variability in cigarettes smoked per day. Like something very descriptive and saying what's going on. A more active title. I've heard some people who put on workshops that I've gone to have been very adamant that it's a bad title if it's passive like this, and that you should have a more active specific title. I'm more indifferent. I think either way is fine, in my opinion, depending on what you're doing. But I get their argument that that can help the viewer better understand what's going on. But I prefer the more passive titles in my own personal use. Okay, so there's our lab title. Let's also get the y-axis label and the x-axis label here. Okay. So diastolic blood pressure, millimeters of mercury. X is systolic blood pressure. Also measured in millimeters of mercury. Okay, we can see those labels show up here. Nice. The legend gets generated because we mapped the size aesthetic to the sig p day variable. We also want to update the legend title here. Okay. And so many of the arguments in labs for customizing labels correspond to the aesthetic that was mapped in AES. So X was specified as connecting to cis-BP, so we specify X inside labs, Y and Y. And so to customize the label for SIGPDAY, we use size. And now you can see that that shows up in the legend. The last thing we're going to add in the labs layer is a caption describing the source of the data set. So another thing that I heard from the data scientists and biostatisticians on social media, they said, you never know where your visualization is going to end up, or if you're in a presentation, giving a presentation, people might wonder often, what is the source of this data? Where did this data come from? Like, I want to look at it myself more in depth. So it's always good it's good practice in every visualization, I think, unless you're using the caption for something else, to have the caption say the source of the data. It's just a good habit to make, and I think can make your visualization more reproducible and people happier that they can understand where that data came from. So here we're going to add that caption. Framingham Heart Study in the Risk Communicator package. So let's maybe knit this document, take a look at how it's looking. Okay, so our visualization nearly is there. It almost reflects what's in the activity. But now let's add a line of best fit showing the linear trend in the relationship between systolic and diastolic blood pressure here. Okay. And so ggplot, as a reminder, is built up in layers. We've already added the points onto our plot. We're going to add these lines of best fit on top of them. And so we can do that by, after geome point, adding a geome smooth layer. Okay. And by default, geome smooth uses a nonlinear fit to show the trend in the data. Okay. But we want to have a linear regression line. So it says here, if you look at the documentation for geome smooth in the method argument, it depends on the number of observations in the data set or what method it ends up using to draw this curve of best fit. So it says across all subsets, across all facets, essentially, this lowest locally fitted, locally estimated smoothing splines is used if there's less than 1,000 observations in each subgroup. Otherwise, it uses a generalized additive model called a GAM, another nonlinear type of model. Okay, we just want a regular run-of-the-mill linear regression. So we say method equals LM for linear model. Okay. Also, by default, the geome smooth method will include standard error bands around the line of best fit. Sometimes you might want those because they express how much uncertainty there is in the model fit, but I typically suppress them because I don't find it important for what I'm wanting to look at. So let's say SE for standard error equals false to suppress those standard error bands. Okay. And by default, the geome smooth line is black through the points. Okay, but that's a little bit hard to see with the black points here. Okay, so we can change the coloring of the line because what happened here is the color aesthetic. Okay, when we specify mapping the color aesthetic to the sex variable, this aesthetic mapping gets applied to all subsequent geomes that are added to our ggplot. So it's happening, these are being applied to geome point, and these aesthetics are also being applied to geome smooth. So the color of the line is varying based on geome, based on the sex of the participant. And then also actually the size of the line is varying based on the cigarettes per day. And how that's happening is the line thickness, although it's kind of hard to see, is varying throughout this line of best fit. So it's slightly less thick in some spots. It's not visible enough to be important though, and it's just too much going on in the plot. So what we'll do is we can force the line thickness to be constant by adding a size equals 1 argument inside geome smooth. Okay, so we run that, and then we can see now size no longer shows up in the legend either. Okay, that was messing up the legend as well. And this is a constant thickness. It looks pretty similar to before. And then we will change the color of the lines just to be constant blue-ish color. So I personally like this Dodger blue color. And RStudio recognizes this as a color name and in quotes, so it actually colors it what it's going to show up as. Kind of fun. Newer versions of RStudio since like a year ago have been able to do that. Okay. So there's our lines of best fit. Okay. And next, what we're going to do is use this function from the ggpub package, which can even add the estimated regression equation that's producing these lines of best fits within each subplot, which is pretty neat. So we can do this by adding this stat regline equation layer. To our previous plot. Okay, let's copy that code chunk. Add this, and we're going to add it right before the theme layer. Okay. And here what I'm adjusting with the label.x, label.y, okay, this is specifying the x position starting point, essentially the horizontal position starting point. I had it right here at 210. You have to play around with that because it can run off the plot, the equation, and ggplot's not very good at recognizing that. And the y position I also had to play around with and toggle such that it wasn't overlapping on the points and was in a good spot in the plot. But you can just play around with these x and y positions to get those equations good. And then the sizes that it controls how big the font is for displaying the equation. But that's pretty much it. It extracts the estimated regression equation components from the same fit that was used to obtain geom smooth with the LM option here. Okay. So we can knit this and take a look. You can see that the equations are nearly the same for both subgroups here. Okay, the slopes are slightly different. The y-intercepts are slightly different, but overall, quite similar. Okay, and we can tell that by looking at the lines, they look quite similar to each other. So the next thing I'll mention briefly real quick is that notice that we do have all these warnings. Okay, we have a warning when ggplot removes the missing values. We have warnings when we loaded packages at the start of the activity. Sometimes you want to suppress those because it's good to see them for the first time, but once you're aware of what the warning is, if you don't care, you don't want it to always display in your report. Note that you can suppress that. Okay, for a given code chunk by saying warning equals false. And sometimes there's messages as well that get displayed from loading packages, so you can say message equals false as well. Just have it be a little quieter. We can add this argument to the ggplot code chunks as well, if you want. Entirely optional, but personally, I find those warnings a little bit of a nuisance. Be a little bit of a nuisance, but once you add warning equals false, cleans up the output a little bit. And let's take a look and see how that looks. Now you can see there's no extra messages there or warnings. A little bit cleaner. Okay. Still give us this message here, but all right. So there's our first visualization for this activity where we have this faceted scatter plot, has a line of best fit, estimated regression equations, okay? And we don't need to interpret model estimates in this class from linear regression, but as like a practice, we would say for males, for every 1 millimeters of mercury higher their systolic blood pressure is, we would expect their diastolic blood pressure to increase by 0.38 millimeters of mercury on average. And we could similarly interpret the value for the females. Notice that the intercepts, the estimated intercepts, we would not interpret those here for a couple reasons. One is that an X value of 0, a systolic blood pressure of 0, is outside the observed range of this data set. Okay, 0 is way out here. So since it's outside the scope of the data set, interpreting it would be extrapolation. Okay, and thus is inappropriate as a reminder. The other reason the estimated intercepts should not be interpreted, because 0 maybe isn't the most sensible for blood pressure, at least for someone who's alive, right? You would hope that someone does not have a 0 blood pressure. So extrapolation and sensibility reasons, you wouldn't really interpret the intercept here. But again, just for modeling, we don't need to interpret estimates in this class, but just know how to add it to a visualization. Okay. So next, let's create these side-by-side box plots showing the total serum cholesterol in milligrams per deciliter for the different combinations of smoking status and the sex of the participants. So that was our scatter plot. I'm going to organize the document here with some headers. I'll call this like faceted scatter plot, and then now we're making a faceted side by side box plot. So we're going to take that Framingham sub data set, type it into ggplot, and we're going to say AES. Okay. If we look at the visualization, okay, smoking status is our x-axis variable, our horizontal axis variable. So that is our x. Serum total cholesterol is our vertical axis variable. So that is our y variable. So x was current smoking status, which in this data set is per smoke. Y, and be careful with the capitalization on these again. Y was total cholesterol. And then we're making a box plot, so we use geome box plot. Okay. Great, that gives us our side-by-side box plot. Okay, then we're also going to increase the overall font size for the axes and title text in the plot. Okay. One way we can do this is by adding a complete theme. We're going to stick with the theme few, and these complete themes from the GG themes package can increase the overall font size by using this base size argument. So that's really helpful because there's lots of different text components to the ggplot visualization. There's the x-axis text, y-axis text, title text, caption text. Okay, if you want to uniformly increase or scale up the font size of all of these simultaneously with nice concise code, we can use this base size argument. And here, let's just make it 16. Okay. The default value, I believe, was 12. So that just makes it a little bit better, a little bit bigger. In general, my advice is to make your font size, if you're giving a presentation and using visualizations in it, to make your font size a little bit bigger than you think is necessary. It's better to have your font be a little bit too big than too small, right? The number of times I've seen other presentations where I feel so bad for the person because, naturally as we get older in life, our eyes unfortunately don't tend to get better. They only tend to get worse. And so if you have people who have a little bit more experience under their belt at your presentation, it's not good when they're like, I cannot see your visualizations at all. Like you need to make the font bigger. That's worthless to me. So I've seen that too many times, sadly, for friends like in grad school, where they got sort of chastised a little bit for not having the biggest font size. And it's so sad because it's such a small, easy thing to control, but you put in all this work to make the visual and maybe a method that you use to analyze the data, but you want to have your visual be readable, right? So try and avoid that issue if you can. Same would go for like interviews, right? If you're showcasing visualizations at interviews, always err on the side of having a little bit bigger font. I think it's a good habit to have. So here, yeah, we're doing that. We're making our font a little bigger. Let's also update the labels for this plot. So we're going to have the x-axis be whether or not they're a current smoker. Y-axis is going to be the serum total cholesterol, which we can see from the help file is measured in milligrams per deciliter. Okay. And then just like before, we can add a caption signifying the source of the data. Just keep it the same exact thing we wrote last time. And our title will just be total cholesterol by smoking status. Something like that. I'm sticking with the passive title again, but if you'd like to tweak it to make it more active, that works. Notice that this is cut off a little bit in the plot preview here. It might still be cut off when we knit or compile the overall document, but it's not necessarily going to be still. Sometimes the plot preview is a little bit distorted or truncated. But you can check by just knitting it. Most important thing is how it looks when it is finally compiled and knit. Okay, the preview is just meant to serve as a little bit of a helpful hint at what it will look like. Here in the final product, no, it's not cut off. It's not truncated. Okay. So there's a good start to the box plots. Okay. Now what we can do is we can color the boxes based on smoking status. By specifying the colors manually. And so we're going to use these medium sea green and royal blue colors. Let's copy that. So let's copy the code from last time. Perfect. And then to manually specify colors, after the geo and box plot layer, we'll add a scale color. a scale fill manual layer, where we say values equals lowercase c, medium C green, and royal blue. Okay. You'll notice this doesn't actually update the colors in the box plot yet. The reason being, we have to map the fill aesthetic to the current smoking status aesthetic. Okay. Hadley, when taking his approach or his philosophy for ggplot2 visualizations and thinking about color, he considers the outline of geometric shapes like boxes to be controlled by the color aesthetic. Okay, so the default color is black here. And the fill aesthetic controls the coloring of the inside of geometric shapes. So in this case, the inside fill, which is white, can be controlled using the fill aesthetic. So here we want the inside coloring to be green and blue. So we want to specify the fill aesthetic and map that to the current smoking status variable. And now that will show up properly in the plot. So the fill aesthetic controls this inside coloring. The default is for the color is black as a reminder, but we're just going to leave that. This is another case of a redundant legend because the x-axis already tells us which group is which for smoking status. So we want to suppress this legend as well. So we can do that by adding a theme layer. Okay, so the theme, just plain old theme layer goes very last. And we say legend dot position equals none. That suppresses the legend entirely. This is a slightly different approach than what we used for the previous visualization, where we used the guides layer to suppress parts of the legend. Okay. This way just suppresses any legend that's showing up whatsoever. Okay, which is what we want to hear, what we want to do here. Okay. So now let's make the title and axis titles bold. So we can do that by using the theme layer. We can just customize the title component, okay, which is a text element of the ggplot. So we use this helper function called element underscore text. And element underscore text, as is shown by the pop-up here, has all kinds of arguments that can control small, fine aspects about this element of the plot. So the title argument controls the overall title, the caption, the x-axis title, and the y-axis title components of the plot. So we can change the font family with the family argument, the coloring of the text. So you could have, for example, let's show that here. And Hadley spells colored with a U because he's from New Zealand, as a reminder. You can control, like, we can make the coloring. I mean, this won't look great, but let's just make it red. So now you can make those components red. Okay. And you can make these components a different color. This is like the x-axis text, okay, of the plot. Oh yeah, we won't change the color here. We just want to make the text bolded. So we can say face equals bold. Okay, and you can make it italicized as well. Bolding is another way to make the labels a little bit more visible. So I generally like to try and do that when showing a visualization in a presentation. So let's knit this one more time. Take a look. This plot is nearly there as well now. You can see the bolding helps make it a little bit easier to read those components of the plot. Let's look. Okay, now we want to facet based on the sex of the participant. Okay, which we can do again using the facet grid function, just like we did before. So let's use facet grid. Add that before the theme layers. Usually that's best to do before the theme layers. Okay, and we are going to make the sex of the participant in the columns again. And now that has our faceted side-by-side box plots showing the total cholesterol by the cross-section of smoking status and the sex of the participant. Next, we're going to make another visualization. This one's going to be a line chart or line graph showing the average number of cigarettes smoked per day by the age of the participant. And then we're going to have different lines for the female and male participants here. Okay. So we're going to show this interesting trend where we have male participants on average smoking more at a younger age than females, but they sort of converge across time. And there's a little bit of a blip here, although there's probably a smaller sample size up in this range of the data. But they end up looking like they converge a bit in terms of how much they smoke as time goes on. Okay. So let's add this plot. I'm going to add a new section. This will be line chart or line graph. Average cigarettes per day by the age of the participant. Okay. So just like usual, we're going to pipe our Framingham sub data into ggplot. Okay. Except this time we're going to do it a little bit different. So we're not going to specify AES inside ggplot here. We're going to add a special stat summary layer where we will use AES and specify the age variable to be our x-axis variable, which is the horizontal variable, and then our vertical axis variable, the y-axis variable, is going to be the cigarettes smoked per day. Now, what's cool about the stat summary function is you can calculate some type of statistic across different values of the data. So for example, here, what we're going to do is we're going to say, we want to calculate for our function of y, fun.y, the function of that we want to apply to the y variable is the mean function. So we want the average or mean cigarettes per day across each value of age. Okay. And so if you run this, I believe this was enough. Oh, no. Didn't quite give enough yet, sorry. Okay, so we're also going to say, let's see. Oh, we want to put this in the wrong spot. Okay, so fun.y goes outside the parentheses here. Yeah, There we go. Fun.y goes outside the parentheses, and then we're going to add the type of plot that it wants to use. In this case, a line chart. So we want to say, okay, make it a line chart and make the line thickness a constant size of 1. There we go. So this plot just shows the average number of cigarettes smoked per day across the age of the participants and just for all the participants at once. Okay. So you can see this trend of, yeah, the youngest people in the data set tend to be smoking the most, and it gradually decreases as people age. This could be for a number of reasons. The visualization doesn't tell us why that's happening. Is it that older people don't like to smoke as much as younger people? Maybe. Could be that people who smoked a lot or like to smoke a lot aren't making it to these ages, right? Maybe these are only the people still in the data set because they didn't smoke as much. Maybe that's what helped them live longer to be included in this data set still at this point. That's a possibility, but we don't know that definitively either. The data doesn't tell us exactly what happened between the variables, but we can just see this trend and do some further digging or hypothesizing about why that might be. Okay. But it's good to note we can't definitively prove anything with this visualization. It's just showing a trend in the data. Okay. So we want to separate the lines based on the sex of the participant here. So one way we can do that is to use the group aesthetic inside AES. So we say group equals sex, and then we're going to color the lines based on the sex of the participant as well. And you get these default ggplot2 colors, not colorblind friendly, as a reminder. Okay. So we can fix that by adding a scale color colorblind layer. Okay. And what's nice about using this again, the females group is getting black, the males group is getting this orange. If we remember back to the visualizations we created previously, okay, we also had males and females. Anytime we have the same subgroups in the data showing up consistently across multiple visualizations, and we use color, we want to be consistent in how we represent those groups with color. It sounds maybe obvious, but it's an easy thing to forget, and it really helps make your visualizations more understandable. So since we used orange for males, black for females here, any visualization such that we have males and females and we can include color easily, we should use these same colors. It helps people follow along, understand what we're trying to show, which is the whole point of a visualization. It's to try and communicate efficiently aspects about our data, right? So we're doing that here. Now we can also add the labels to update the plot labels here. Okay, so let's add a labs layer. We could say age in years. It's a little bit obvious, I would hope. It's not like months. Wouldn't hope children are smoking, but yeah, it happens, I guess. We'll just call it age. Average cigarettes per day. And then the color aesthetic, which will update the legend title. Okay, we're just going to make it all, not all caps anymore. Okay. There we go. We can add that caption in if we want. Perfect. Okay. So now we're nearly there. Let's apply a different complete theme to the plot and have the axis show the breaks at 0, 4, 8, and 12. So 0, 4, 8, 12, 16. So ours, notice how it's showing breaks at 0, 5, 10, and 15. Hadley just wrote some code to pick these cut points automatically. And there's nothing particularly wrong with these values here, but we're just showing how you can customize that. Maybe you had specific breakpoints that are meaningful and important to show. So we can customize that. So let's customize those breakpoints. And we can do that by using a scale Y continuous layer. So notice how we used the scale colorblind layer to customize aspects about the color aesthetic. We use scale Y continuous to customize aspects about the Y aesthetic, and continuous is used when Y is numeric. Okay. So there's also a scale X continuous layer. There's a scale fill colorblind layer for the fill aesthetic. Okay, there's lots of scale layers that you can add to finely customize aspects about aesthetics and ggplots. So for scale Y continuous, to specify the cut points or the breaks, we use the breaks argument. And then you just give it a vector of values where you want the breakpoints at. In this case, we want 0, 4, 8, 12, 16. So we can supply this vector here. If you paste that in the console, you can see it's a vector of numbers. You can also create vectors of numbers using the seq function for sequence, SEQ. So you can say from 0 to equals 16 by equals 4. Okay, and that gives you the same sequence. The seq function can be really useful if you have a really long sequence. Like you could go 0 to 100 by 25, for example, or by just 5. Okay, it can, instead of having to type all that out, maybe you have a lot of cut points or other operations in R you would need a vector of numbers for. Okay, the seq function can be helpful. Here we're just going to manually specify those breakpoints. Okay, and you can see in the resulting visualization, it goes now 0, 4 up onto 16. Okay. And then to apply another complete theme, to change what the complete theme is, we can add a layer. There's all kinds of themes from GG themes. Let's try like the, well, let's see if 538 works. Sure. Maybe not the prettiest looking theme ever. Oh, and the font gets too big for the title, it looks like, probably. Well, let's just stick with the theme view. Okay, even though that doesn't actually change what the base theme is, since we specified it earlier, we'll just stick with that. You might have to tweak the base font size if it gets too big, depending on your chosen theme. But feel free to choose whatever theme you would like, of course, whatever floats your boat. Okay. Let's take a look at it knitting here. All right. So we have this nice line chart over time showing the trend in the average number of cigarettes smoked per day by the age of the participant, stratified by sex. Okay. So note that we could have used another statistic here besides the mean. The mean or average is sensitive to outliers. But if you used the median, could be a very different story in terms of how it looks, right? Median, the 50th percentile is less sensitive to outliers. So you might have a very different looking result. Always something to keep in mind. So now that we've created a few visualizations, let's combine some of these together. So we're going to do that using the patchwork package. This is the newest package available for ggplot that allows you to combine multiple ggplot visualizations into a single image. Okay. So for example, we can combine the line chart and the faceted scatter plot all together into a single image using the patchwork package. Okay. So let's do that. Okay. And to do so, what we have to do is we want to store our ggplot visualizations in objects that show up in our environment. Okay, so whenever you have a ggplot, for example, with our line chart, you can store it by going to the very left-hand topmost part of your code. We'll call it, say, line chart. You can pick any valid R name here. Maybe we'll call it gg underscore line chart. Okay, gg underscore line chart. If you run this code now, it does not display the visualization because it's getting stored in this object called gg line chart. So you'll notice this shows up as a list type element with 11 items in the list. Okay, you can click on it and kind of open it up. It's a list of length 11. The first item of the list is the whole data set that was used to make the ggplot. You have the different layers you can access and different components of those. Okay, the labels, you could go back and modify those. Okay, a ggplot is unique in that we can store it in this object like this. You cannot do that with base R visualizations or plots made not with ggplot2, okay, for the most part. So this is nice because you can store it and then modify this visualization later. So if we still want to display it here, we can just print the name of the object below our code. And now that will still display the ggplot here, the line chart, but keep it stored as an object. Okay, we're going to need this object that was stored to combine it with the patchwork package and the other visualization later. So we're going to do the same thing with the other visual, which was the faceted scatter plot here. Okay, so if we go up to the faceted scatter plot, yep, right here, let's call that gg scatter. So we're going to store this in gg scatter. Okay, see how that shows up as its own list. And then we're going to still print gg scatter below this code to still display it here. Okay. But now both of these objects are in our environment and we can refer to them to combine them using the patchwork package. So the patchwork package is wonderful for its simplicity. To stack two charts on top of each other, all we have to do is make sure the patchwork package is loaded, which we actually already did at the top of our activity, so this is not necessary. It's a little bit redundant. But once it's loaded, we give the name of the ggplot object that we want on top, and then the name of the ggplot object that we want on the bottom. Now it'll look crowded in the plot preview. It looks absolutely awful, right? Doesn't look quite as bad when we knit the document, but it still needs a little bit of tweaking. So if we do this here, looking at the compiled document, compiled report, it's still a little scrunched, right? So we'll fix it up a little bit here. So one thing to note, there's a caption for both of the visuals, but now that it's combined, only one caption is needed. This first caption's a little redundant. So let's get rid of that caption for the line chart. That'll help it from being so scrunched. So let's just get rid of the caption part. Now if we recompile it again, we can see how it looks with that redundant caption removed. And sometimes it still is too scrunched, right? And so this can kind of be a little bit of a pain, a little bit of a thorn in our side about getting it to look okay. So notice how it's still overlapping, for example, these labels. That's not ideal. So we can try and play around with like the figure sizes to get that fixed up. For example, using the code chunk options, we can say like fig dot height equals 6, fig dot width equals 6. You can kind of play around and toggle these values until the plot is not having overlapping labels anymore. It's kind of annoying because sometimes it can be a little bit tedious. But that's how you know you're a true ggplotter, is because you're messing around with the fine little dimensions and plot labels. Part of the fun, right? Okay, so I spared you all that and played around with those numbers a ton myself until it was like, okay, it's not overlapping a ton anymore. So yeah, and so sometimes there's a benefit to having one cohesive image versus just displaying the two right next to each other. Like maybe you want to save this for a publication and it's a single figure you're referring to. So that can be helpful. Maybe the plots are very much tied together or married together. So it's important to have them in one single image. It's nice that Patchwork has that simplicity. So you can stack images on top of each other, ggplots on top of each other by using the divided by symbol. You could add them side by side using a plus symbol. This will look awful because they're just too wide, but just to show that you can do it. Right, they're too scrunched, but you can do side by side with a plus. You can have like one plot up top, and you can have two in the bottom, for example. I believe it works like this. Let's see if it accepts that syntax. Yep. Okay, so I have like the one plot on top, the line chart, and then the scatter plot and the line chart on the bottom. Okay, so you can kind of do complicated combinations of multiple visualizations into a single image with Patchwork. And it's really nice. It simplified the code for this compared to earlier R packages that attempted to do the same thing, but required a little bit more complex code. So notice that, again, as a reminder, this type of syntax only works with ggplots if you have the Patchwork package installed and loaded. So that was combining plots with Patchwork. For Our next visualization here, we're going to make a bar chart, a horizontal bar chart, showing how many participants fall into the different cholesterol categories. So for this bar chart, we're going to be looking at using this definition from Johns Hopkins Medicine that categorizes all people, just regardless of age, sex of the participant, lots of different factors. That just says if your cholesterol is less than 200 milligrams per deciliter, your total cholesterol, then it's considered normal. If it's between 200 and 239 inclusive, it's high. And if it's greater than 240, it's, or I'm sorry, borderline high. And if it's greater than 240, it's considered high. Of course, this is an oversimplification. You should consider lots of other factors about people, and categorizing everyone uniformly into these is not ideal, but we're just going to do it for the sake of demonstrating how to create a bar chart here, faceted bar chart. So to start, we have this total cholesterol variable. We can create this categorical version of this variable. We're going to call it cholesterol cat for cholesterol category. And we're going to use case one and mutate again, okay, to say when it's less than 200, it's normal, greater than or equal to 200, and total cholesterol is less than 240. We're going to say borderline high. And if it's greater than 240, we just say high. Okay, so let's copy that code. Okay. So we can see if we look at the Framingham sub data set, we can look at that variable. See, yep, 195 is normal, 209, yeah, borderline, 250 is above 240, so it's considered high. Yep, so it seems like it worked. And then when the total cholesterol is missing, understandably and naturally, the cholesterol category is missing. So now that we have that variable created, we can create a bar chart showing how many people fall into each cholesterol category. So we can use geom bar to do so. We'll also remove or filter out people who are under 40 years old and those who do not have recorded cholesterol levels, essentially missing values for the cholesterol category, using this code that involves use of the filter function. So let's take our Framingham data to start, pipe it into ggplot, and our horizontal axis variable here, our x-axis variable, is cholesterol category. So we're going to say x equals cholesterol cat. And then when we have a categorical variable that we want to make a bar chart for, we can specify the x aesthetic as being mapped to that variable and then add a geom bar layer. This automatically tallies up and creates a count for each group. Okay, notice we have the missing values here, so we can remove those by adding this filter layer before we piped into ggplot. Add its own pipe there, And then since there's a lot of functions called filter from different packages, to be safe, we want the filter function from the dplyr package, so we can use dplyr : filter. This just makes sure it's calling the correct filter function so that you don't get a weird error, because other filter functions take different arguments and behave differently, potentially. So this is only keeping observations where these conditions are true, where age is at least 40 and where the cholesterol category is not missing. So this is the negation operator or the not operator. So for example, if we check is 3 less than 5 in R, like in the console, this returns true. Yes, 3 is less than 5. If we negate this logical condition, if we say the negation of is 3 less than 5, it flips a true to a false. And conversely, it would flip a false to a true. Okay. So the is.na function checks, is something missing? Is it an na value? And so we're saying where it's not na, we want to keep those rows. If we run that code, now we've filtered out all the missing values and people who are under 40. So that's a good start. Let's fix up some of the labels here. So for the title, you can say that. X we'll call cholesterol level. Y we'll say it's count with a capital C. And then we can add the same caption like usual. We can just steal that caption from earlier. There we go. All right, looking better. Now, notice that by default, the bars are not sorted in an order that we'd like. Okay. There's two possibilities when making a bar chart for a categorical variable. You either have a nominal categorical variable where there's no particular ordering or natural ordering to the categories. An example of this would be the sex of the participant. There's no particular ordering to those categories. They could go females then males or males then females, and that would be fine for this data set. Another example would be majors that students are studying in school, like math, statistics, writing, English. Those don't have any particular order, so it's a nominal categorical variable, the major of the student. You can also have an ordinal categorical variable, where there's a natural ordering to the variables, to the categories of the variable. Like in this case, the cholesterol levels, normal, borderline, and high, those have a particular ordering. Normal is less than borderline. Borderline is less than high. So whenever you have an ordinal variable in a bar chart, you should nearly always, unless you have an extremely strong reason otherwise, you should nearly always sort the bars based on that natural ordering of those categories. R doesn't recognize that this really should be ordered as normal, borderline, high. So we have to tell it that explicitly. Okay? And we can do that using the factor relevel function inside the call to ggplot. So we're right here where we have x equals cholesterol cat, we can use this fct underscore relevel function and wrap that around with parentheses. You'll have to be careful of your parentheses here. wrap that around the cholesterol category, and then after the variable name that we want to re-level. So a factor variable, as a reminder, is kind of similar to a categorical variable in R. So we're redoing the levels or the categories of this factor variable. We save the variable name, and then we list the categories in the order we want them to show up as. And you have to be very careful about the capitalization here and how we spell these levels out. It has to match the data exactly. Otherwise, it'll cause an issue in your visualization that's hard to catch because it doesn't necessarily cause an error. It just won't do what we want it to properly. Okay. So in Framingham sub, it's spelled as normal with a capital N. So be careful of the capitalization. Normal with a capital N. Then we want borderline high, which is spelled with just a capital B. Okay, so again, be very careful of the capitalization, and then high with one capital H. Now, if you run the code, the bars will be sorted properly based on how we want. Okay. If they're still not sorting properly for you, I would check and make sure that your spelling with the capitalization is matching these exactly as they're supposed to be. That's a common mistake here. So now that we have reordered the categories here, we can also change the inside coloring of the bars. Okay, and so as a reminder, this is similar to the box plots where the fill aesthetic is controlling the inside coloring of the shape. The color aesthetic controls the outline coloring of the shape. So to change the inside coloring, we use the fill aesthetic here. So we will say inside AES, we will say fill equals, and we want fill to be a function of the cholesterol category. And Hadley will give us some default ggplot2 colors for those. Again, not colorblind friendly, so we want to update those. So we're going to add a scale fill Viridis D layer, where D stands for discrete. Okay. So Viridis is the name of the color palette or the set of colors, and Viridis is a colorblind friendly color palette. Okay. Fill is controlling the fill aesthetic, and D is for discrete. So when we run this, we get this yellow, purple, and tealish color that are colorblind friendly. Another great example of the legend being redundant here, so we will suppress this using the theme layer. That suppresses the legend. And then we will change the outline coloring of the bars because by default, Hadley has the color for bar charts update to match the fill for each bar. But to make the bars a little bit crisper looking, we'll just set the outline to be black. It just makes them a little bit crisper in the image. It's my personal preference. And then we'll facet by the sex of the participant. Okay, just like we've been doing previously, we will use, before the theme layer, asset underscore grid. Okay, just like that. Perfect. Okay, so we can see for males in this data set, those who identified as males in this data set, the number of people with borderline high cholesterols is similar to high, both higher than the normal category. But for women, for the females, it's much higher for the high bar relative to the other two. Okay. Again, why that's happening or what's causing that to happen. Okay, we can't conclude that from this plot, but just visually, that's what's happening. And it's important to note that we excluded people under 40. We excluded people with a missing cholesterol value. Okay, so there's certain caveats there too in terms of what we can take away from this plot. But that's how we make a faceted bar chart here. Another thing that's a little bit annoying about ggplot is whenever you make histograms or bar charts like this one, by default, the bars kind of float in space a little bit here. It's a little bit strange because the bars, at least for this plot here, because they're counts, could not be smaller than 0. So really the x-axis should start exactly at 0. It's a small thing, but it's a little bit annoying about ggplot. So we can get rid of this superfluous extra space here as well. Okay, and we'll do that by using a scale y continuous layer. And we'll say expand equals expansion mult equals combine 0, 0.1. Okay, little lowercase c for combine. So what this is doing, sadly, I have this memorized because I had to Google this code so much. Okay, it gets rid of that extra space there. What this is doing is it's saying expand the y-axis variable by a multitude or a multiplicative factor, I should say, of 0% from the bottom of the bar. So 0% extra space below the bar. And then for the tallest bar, expand the plot by 10% or 0.1 of its height. Okay, so it's added 10% of the height of the tallest bar. You could see if you changed this to 0, it would have no space above the tallest bar, which looks a little funny. So usually I like to add just 10% of space. That way it scales to any data set decently well. Okay, just above that tallest bar. That gets rid of the superfluous space there. Now, it's not an issue here, but sometimes you have so many categories or the names of the categories are so long that they just overlap each other. And ggplot doesn't care. It will just print them all on top of each other, throw you out the plot and say, hey, it's good to go. But we don't want text to be overlapping, jumbled on top of each other. So there's a couple ways we can fix it. You can angle the text at like a 45-degree angle so that they don't overlap as much. You can decrease the font size of the text, although that's not ideal because then it's harder to read. Or my recommended approach would be to turn this into a horizontal bar chart where we essentially flip the x and y axis variables. There's no meaningful difference between the two types of plots, except a vertical bar chart just tends to be a little bit more common, but switching to a horizontal bar chart, you can have a very large number of categories with long names and they will display okay. They won't overlap each other. Okay. So we can do that. We can flip this to a horizontal bar chart like this by using a chord flip layer. Okay. And we'll add that right before the theme. Just like this. Now we have a horizontal bar chart. And it looks great. Okay, so let's knit that. Well, that's knitting. Okay. Note that this is one way to visualize this data. An alternative way to visualize the number of people in each of these categories is to use a faceted dumbbell chart, okay, which you can make by essentially using geom point and geom line. Okay, this is a little bit of a challenge, so I'm going to have this be an optional part for the activity, but just know that you could go ahead and try this if you wanted, although Certainly by no means required. Okay. But that's an option if you want a challenge to try and make this dumbbell chart to show that same data. Okay, some argue it's better than the bar chart because it uses a lot less ink if you were to print it, for example. Not that people print as much these days, but best data visualization practices generally are to make visualizations with the least amount of ink possible, with the goal of it being more efficient or easy to understand. Okay, but that's optional. What we'll do last here is give you this you try part. So go ahead and pause the video here and try to make this line chart by modifying the code we wrote previously. Okay, so we had that code that got the average cigarettes per day across the age of the participant by the sex of the participant. So try and modify that code, copy it and modify it to get the median body mass index across the age of people and reproduce this plot here. Okay. So you may need to use a scale X continuous layer to help you specify these breaks if these breaks don't work out nicely for you. A scale color manual layer is how you can match the coloring here. Okay. And you may need to filter the data to subset to only people with ages between 40 and 70. Okay, as a hint. But go ahead and pause the video and try that out on your own. Okay, hopefully that gave you some time to try out making this line chart. So let's make it on our own here. So we're going to make this chart showing the median BMI across ages of the participants. Let's copy our code that had the line chart, right? I want like GG line chart, maybe like BMI. Okay, so we'll update that in both the spots here. BMI, BMI. And let's think about what we need to change. So we want to filter the data, only have those whose age is greater than or equal to 40 and age less than or equal to 70. We want to have BMI instead of cigarettes per day. Okay, and so we'll change the labels to say median body mass index. Current smoker. Okay, we also want the group to be per smoke instead of the sex of the participant. We'll change the title to say we can add the years on here since it's body mass index now. Okay. We can get rid of the scale Y continuous breaks layer. And instead of scale color colorblind, we'll use scale color manual to say, and we'll get the same colors as we used before for the smoking statuses, so the medium sea green and royal blue. Okay. And then, let's see. Oh, we want to get rid of the legend. So we'll say theme legend dot position equals none. Make sure this goes below your complete theme. If you applied one, it should be the very last layer we add to our ggplot with the plus sign. Or I'm sorry, we want legend dot position equals bottom, not none. Okay. And oh, we can add a caption. Copy that caption from before. Perfect. Okay, I probably have an error in here. Let's see how it we just did. Oh no. Okay, it's looking pretty good. So we've got, let's see how it looks compared to the activity. Body mass index 24 to 26.5. Not bad. Age goes 40 to 70. Yeah. Nice. Median BMI by age and smoking status. Current smoker. No, yes. Yeah, it's looking good. Okay, let's knit that and see how it looks. I'll keep showing the code here. All right. Perfect. So we could modify the breaks as well if we wanted to match it by using scale Y continuous and getting those custom breakpoints. I think these breakpoints actually look nicer. So we'll just keep it at that. Let's see. Group, let's make sure the code is correct here. First milk, yep. Age, BMI, yep. Line. Oh, okay. One thing I forgot. Instead of mean, we want the median. So median. Okay, instead of mean, this tells it to use the median function. Okay, now, yeah, that's why it was looking a little different. There we go. Yes, there we go. Mm. And now we can see that similar trend to what we see in the activities visualization. Okay. So like I said, this last part with the dumbbell chart is optional. You don't have to try it. But otherwise, that concludes this activity on data visualization with ggplot2.